title of the module, Complex Roots of Unity. In this module, we are going to see about the complex roots of unity, which is also known as a de Moivre number, and it is basically a complex number which when raised to some integer n gives the result as 1. Let us see the definition. The complex root of unity is a complex number which is a solution of the equation z power n is equal to 1 where n is greater than or equal to 1. Let us solve this equation. So, z power n is equal to 1 can be written as z is equal to 1 power 1 by n. So, we know that 1 can be written as cos 2k pi plus I sin 2k pi, the whole power 1 by n. Let us apply the de Moivre theorem. So, this becomes cos 2k pi by n plus I sin 2k pi by n. So, the solutions of this equation will be of this form: omega power k is equal to e power I 2k pi by n, where k is equal to 0, 1, 2 up to n minus 1. So, these are the solutions of this equation z power n is equal to 1. The following theorem will show you the sum and the products of the roots of unity. If omega, omega squared, omega cubed, so on up to omega power n minus 1 are the nth roots of unity, then 1 plus omega squared plus so on up to omega power n minus 1 is equal to 0. That is, the sum of all the roots is equal to 0 and the product of all the roots of unity is equal to minus 1 the whole power n minus 1. We shall now see the proof of the theorem. 1 plus omega squared plus so on up to omega power n minus 1 is equal to 0. We are going to prove this result. So, we can clearly see that this is forming a geometric sequence and this is having the common ratio as omega, and therefore, we know that the sum of these terms is equal to omega power n minus 1 by omega minus 1. We know that omega power n is equal to 1. So, 1 minus 1 by omega minus 1. So, clearly this is equal to 0 and therefore, we have proved the first result. Now, we shall prove the second result. 1 times omega into omega squared so on up to omega power n minus 1. This can be written as omega power 1 plus 2 plus 3 so on up to n minus 1. So, we know that this is equal to omega power n into n minus 1 by 2. So, this can be written as cos 2 pi by n plus I sin 2 pi by n the whole power n into n minus 1 by 2. Now, let us use the de Moivre's theorem. So, using the de Moivre theorem, this particular power comes inside and therefore, this becomes cos 2 pi by n times n into n minus 1 by 2 plus I sin 2 pi by n into n minus 1 by 2. So, this is equal to, cancelling the terms, we are left with cos pi into n minus 1 plus I sin pi into n minus 1. We know that cos pi is equal to minus 1. So, this is nothing but minus 1 the whole power n minus 1, and thereby we have proved the result, that the product of the roots is equal to minus 1 the whole power n minus 1. Now, we shall see the next theorem. The set un of complex roots of unity is an abelian group under usual multiplication. So, in order to prove this, we will have to check the group for certain properties. So, first one is closure. Clearly, omega power n plus t is equal to omega power t. So, why we do this is because if any one of the two terms, let us say omega power a times omega power b, one of the terms is greater than n, this can be written in this form omega power n plus t, and automatically omega power n becomes 1, and so we are left with omega power t where t is greater than or equal to 1. So, again this term is again within the group and therefore, the closure property holds. The property number 2 is associativity. Here we take 3 different terms, omega power a, omega power b and omega power c, and clearly we can see that this is true and omega power A times omega power B the whole times omega power C is the same as omega power A times omega power B times omega power C. So, associative property also holds. The third property is identity. So, for that let us assume that omega power 0 is a term that we take here. So, omega power A times omega power 0, this is the same as omega power 0 times omega power A. The product of these two terms is equal to omega power A. So, we have identified the identity of the group which happens to be omega power 0 and that is equal to 1. And the inverse property omega power t, for any root omega power t, the inverse should be omega power n minus t, and this is same the either way around, and this is equal to omega power 0 which happens to be the identity element, and therefore, we can say that omega power n minus t is the inverse element of omega power t. Then property number 5, we have to show that this is commutative because we need to show that this is an abelian group, and therefore, commutative property is omega power A times omega power B. This is clearly equal to omega power B times omega power A, and therefore, we have now proved that because the group satisfies all these properties, we can say that the set UN of complex roots of unity is an abelian group under multiplication. Now, we shall see some of the properties of the complex roots of unity. So, Z is equal to cos 2k pi by n plus I sin 2k pi by n, and therefore, Z is equal to r e power I theta. Now, this is the standard polar form, and we are going to compare this along with this, and we realize that r is equal to 1, and this shows that Z lies on the unit circle, and because of this the period of omega power I is equal to 2 pi by n. And now, when we are doing the calculations, and let us take n is equal to 1 and Z is equal to 1 here, and we realize that the root is just one root 1 comma 0. We represent this on the complex plane, and the complex plane can be represented as the x axis as the real part of Z and the y axis being the imaginary part of Z, and since the root is only 1 comma 0, it lies on the real plane which is here. So, the imaginary part is 0 and therefore, it is 1 comma 0. So, next we check the values for n is equal to 2. Therefore, that means Z power 2 is equal to 1 because the equation is Z power n is equal to 1 and we have taken n is equal to 2 here, and that becomes Z is equal to cos 2k pi by 2 plus I sin 2k pi by 2. So, the 2 gets cancelled and we are left with cos k pi plus I sin k pi. And clearly, the roots of this particular equation is minus 1 comma 0 and 1 comma 0, and they can be represented on the unit circle like this. So, 1 comma 0 here and minus 1 comma 0 here, and on the complex plane this is the real part of Z, this is the imaginary part of Z, and clearly we can see that they are separated by a distance pi which is 180 degree, and therefore, Z has period pi. Next, we take n is equal to 3. And therefore, the equation is Z cube is equal to 1. Therefore, Z can be written as cos 2k pi by 3 plus I sin 2k pi by 3. Now, when k is equal to 1, it becomes cos 2 pi by 3 plus I sin 2 pi by 3. So, the roots are 1 comma 0, minus 1 by 2 root 3 by 2 and minus 1 by 2 comma minus root 3 by 2. So, cos 120 degree. So, we can check that, and when we are plotting this on the unit circle in the imaginary plane and the real plane, and this becomes minus 1 by 2 comma root 3 by 2 lies here, and minus 1 by 2 comma minus root 3 by 2 lies on the entirely on the imaginary plane here, and of course 1 comma 0 is here. So, clearly you can see that the period is 2 pi by 3, and therefore, Z has period 2 pi by 3. Next, for n is equal to 4. So, the equation is Z power 4 is equal to 1. Again, we write Z is equal to cos 2k pi by 4 plus I sin 2k pi by 4, they get cancelled, and so we are left with cos k pi by 2 plus I sin k pi by 2. And this equation has 4 roots, namely minus 1 comma 0, 0 comma 1, 1 0 and 0 comma minus 1. So, basically all the 4 corners of the unit circle, and when we have plotted all the 4 points here, and this is the real part of Z and this is the imaginary part of Z. So, you can see that in every quadrant, and the period is pi by 2. So, this is 90 degree, 90 degree, 90 degree and 90 degree. So, the period is pi by 2. Now, when n is equal to 5, it becomes Z power 5 is equal to 1, z is equal to cos 2k pi by 5 plus I sin 2k pi by 5. There are going to be 5 roots. Once again, they are all going to be lying on the unit circle with the real part of z being here and the imaginary part of z being here and the period being 2 pi by 5. You can even take it as an exercise to verify what are the roots lying on the unit circle. So now we come to the general case. Z is equal to 1 power 1 by n, and therefore 1 can be written as 1 plus I0. This is nothing but e power I0, the Euler format. And we realize that when we do a 2 pi radian revolution, we get e power 2 pi I, and after 4 pi radian revolution it becomes e power twice of 2 pi I. So in general, z is equal to e power 2k pi I by n the whole power 1 by n, k equal to 0, 1, 2, so on up to n minus 1. The point of this exercise is to show that all the roots of 1 power 1 by n, the complex roots of unity, lie on the unit circle, and depending on this, the period also changes depending on the value of n. Now these are some of the important things to note about this. So omega power I conjugate is equal to 1 by omega power I, which is equal to omega power n minus I. The second note is z power n minus 1 can be written as x minus 1, x minus omega squared. We can write it in this manner because we know that the roots of z power n minus 1 equal to 0 are 1, omega squared, so on up to omega power n minus 1. So we write it in the form of factors, and therefore this can be further written as z minus 1 times z power n minus 1 plus z power n minus 2, so on up to z plus 1. So x minus 1, x minus omega, and so on. And clearly this can be cancelled, and you are left with 1 plus z squared plus so on up to z power n minus 1 is equal to, substituting instead of x we use z, so z minus omega squared, so on up to z minus omega power n minus 1. Now keeping this equation aside, let us go to a problem. We are given a problem where we have to solve that 1 plus x squared plus x cube is equal to 0. We shall consider the fourth roots of unity. So z power 4 is equal to 1. We know that the solutions are 1, minus 1, I and minus I, but we have only the up to 3 here. So x power 3 is the maximum power here, and therefore the 1 cannot be a root of this equation, and therefore let us consider n is equal to pi r equal to 1 to n minus 1, 1 minus omega power r. Therefore the roots of this equation can only be minus 1 I minus I, and we shall solve this. The magnitude of z is n is equal to the product function of 1 minus omega power r. So we know that these are the roots of the complex roots of unity, and therefore the product of all these will give you n, and the pi function r equal to 1 to n, 1 minus omega power r. So pi r equal to 1 to n, 1 minus e power. So we know instead of omega power r we can substitute e power 2 pi I r by n, and therefore when we take a 2 term outside, we are left with 2 power n minus 1 on the outside. Product function pi I r equal to 1 to n sin pi r by n. So this we get by cancellation of terms after substituting cos in sin terms and cancelling, and 2 power n minus 1 pi r equal to 1 to n sin pi r by n. So the modulus function is no longer necessary, it becomes obsolete, and here we are left, there is an n here. So this 2 power n minus 1 can be taken to the left hand side. N by 2 power n minus 1 is equal to the product of r equal to 1 to n sin pi r by n. Now let us apply r equal to 1, 2, etc., and so we are left with sin pi by n times sin 2 pi by n, so on up to sin n minus 1 pi by n is equal to n by 2 power n minus 1. This result will be used in the next problem. Now this is the result we just derived, and this is the problem we are going to do. We have to find the value of sin pi by 7, sin 2 pi by 7, sin 3 pi by 7. So the product of these 3 terms. So we know this equation. Let us put n is equal to 7 in this equation. So in that case we get these equations: sin pi by 7 times sin 2 pi by 7 times sin 3 pi by 7, sin 4 pi by 7, and so on up to sin 6 pi by 7, because n minus 1 pi by 7, and n by 2 power n minus 1, therefore we get 7 by 2 power 6, and sin pi by 7 sine 2 pi by 7, sine 3 pi by 7, we can keep it as such because they are the required terms given in the problem. But sine 4 pi by 7 can be written as sine pi minus 3 pi by 7. If you calculate, it becomes 7 pi minus 3 pi, so it is 4 pi by 7. And so, sine pi minus 3 pi by 7, sine pi minus 2 pi by 7, sine pi minus pi by 7, and therefore, instead of these terms we have substituted like this. And in this case, we know that sine pi minus theta is sine theta, and therefore, these terms also become sine 3 pi by 7, this becomes sine 2 pi by 7, this becomes sine pi by 7, and therefore, when you take the product, it becomes sine squared pi by 7, sine squared 2 pi by 7, sine squared 3 pi by 7. The right hand side is carried on, and we need to just find the square root in order to find the value of this term. So, we take the square root, and so we have root 7 by 2 cube is equal to sine pi by 7, sine 2 pi by 7, sine 3 pi by 7, and therefore, we have found the solution of this term. In this module, we saw about the complex roots of unity, which are nothing but the roots of the equation z power n is equal to 1. We also saw how these roots form an abelian group, and therefore, whatever properties apply to abelian groups also apply to the complex roots of unity, and therefore, the complex roots of unity can be considered as a special example of abelian groups. The n roots of unity always lie on a unit circle. Now, this is another property that we saw, and we also saw some of the problems related to these properties. I hope that this module was useful to you. Thank you.